All right. So, okay. So, first thing for this force problem, what do you want to do? Say it louder. Free body diagram. Very good. Okay. So, start over here. What's the free body? The dude. Okay, the person. So, raise your hand if you can tell me one of the forces acting on him. Mark, which way? Very good. Okay, who's got another one? Josh, which way? No. Okay, good. So we have a tension force to the left. All right, Garrett. Which way? All right, very good. What kind of friction force? Static. It's keeping his feet from falling out from under. Remember, if you're trying to figure out which way friction is pointing, you got to say which way would this guy be more likely to move, right? If this tension force is pulling on him, his feet are going to slip out from under him that way, which means friction is going to pull on him this way, all right? Okay, it would oppose the possible motion there, okay? All right, let's see, I need another one. Isaac? Very good. There's an upward tension force.
I have a question.
It's like a circus performer or something. What's up?
When he did pull the string, like from above, wouldn't his like feet slide? He just like slam on his back on the floor. That's if there wasn't enough tension in the rope already to keep him at like an angle to catch himself and just hold himself up.
Maybe he could. Yeah.
If there wasn't enough rope for him to fall all the way down, and what about he's just working on his core, guys.
It's an awesome workout there. Okay, we're missing one more force. There's one more force here. Very good. Which way? Up. Okay. Shh. Hey, y'all been awfully talkative today. Not cool. All right, so now we have our free body diagram. So what's the next step? FNet statements, okay? I want to read through the problem so we know what we're actually supposed to be finding here. What's up, Graham? No, we actually need to know that they're both the same tension force because they're all part of the same string. Okay? Yeah, because in that case we had two separate systems, two things we were looking at. This one's just one thing. Both of those tension forces are acting on the same object. All right, so a 70-kilogram person ties a rope around their feet and then feeds the rope over a series of pulleys so that they can pull on the other end of the rope over their head. The coefficient of friction for the ground they are standing on is 0.4. What is the tension in the rope when their feet slip out from under them? Okay. All right. So let's see here. What axis are we going to play with first? X-axis. All right. So we'll do our FNet statement in the X-axis. What's the first FNet statement going to be? In the X-axis. Very good. Okay. What is the acceleration in the X-axis? It's 0. Okay. All right, so what are we going to have here? 0 newtons, okay?
I thought we were solving the story moving.
Yeah, it says when their feet slip, right? So at the exact instant that his feet are starting to slip, that starting point was 0, okay? All right, so then we've got the next FNet statement. I'll move up a little bit here. Our next FNet statement is going to be what? Very good. Sum of all the forces in the X-axis. And raise your hand if you can tell me what are all those forces. Okay. Hold on just a second, then I'll come back to you. Garrett? Very good. Fs minus Ft. Final thing, what do we do? Set them equal to each other. So friction force minus the tension force has to equal 0 newtons.
So should we get a negative number then?
Very good. Friction equals tension force. No. Okay, Adam, what's your question? Right, his feet are going to start losing contact with the surface. They're going to start coming up a little bit, but in this class, we're not concerned with that. We're just concerned with his feet are being pulled on by that tension force in this direction, because that rope that's pulling up on him, we're going to say that's affecting the hands part of his body, and the rope that's down there touching his feet, that's only operating the x-axis for right now, for our purposes. Okay. All right, cool. So we've got our first equation there, right? Do we know the friction force? Okay, well, you do? What is it? What's the friction force equal to? Yeah, mu times the normal force, okay? So this friction formula here, very good. Mu times the normal force, all right? So I'm going to kind of expand this. I'm going to say then that, bless you, the tension force is equal to mu times the normal force. And now normal force. What axis is that in? The y. So we'll need to go on ahead and do our F net statements in the y-axis then. Okay. So F net in the y-axis. What's the first F net statement going to be? In the y-axis. Very good. What is the acceleration in the y-axis? 0. So what's this first statement equal? 0 babies, pineapples, newtons. Very good. Okay. All right. Next F net statement in the y-axis is what? Sum of all of our forces, okay? So if we go back and we look at our free body diagram, what are all the forces in the y-axis? Very good, okay? All right, so we've got the tension force plus the normal force minus the force of gravity. What do I do with those two? Okay. Oh. Okay, now what are we trying to solve for here? Normal force, okay? Without the normal force, we can't find the tension force. So tell me what I should do here. Okay, let's add the force of gravity to the other side. What else? Yeah, we'll subtract the tension force. So that means that normal force is equal to the force of gravity minus the tension force. Everybody cool with that? All right, now we're going to make a substitution into that previous equation. Previous equation said that the tension force was equal to the frictional force, which was equal to mu times the normal force. So that's equal to mu times the force of gravity minus the tension force. Everybody okay with that? What we just did there? We took our stuff here for normal force and plugged it in right there. Is that okay? All right. So now you'll notice that we have two tension forces in the same equation. And I'm going to go ahead and expand the equation here for Fg. What is that? What's the formula for force of gravity? Mg. So I'm going to say mu s times m times g times, or excuse me, minus force of tension. Okay? Now, what do you want to do? Well, we're not set up correctly for that yet. We have tension force on both sides of our equal sign. That's not good. Okay, bless you. Well, yeah, we actually have to distribute before we can do that, right? There we go. All right, so we're going to distribute our mu s to all of these things here. Okay, so that means we're going to have the force of tension equals mu s times m times g. Okay, I'm just factoring out the mu s from both of those, and then I'm going to say minus mu s times tension force. Everybody okay with what I just did there algebraically? Okay. Now I'm going to go ahead and add this term to the other side so I can group my tension forces. No, they're exactly the same tension force, okay? All right, so tell me what you think I should do there then, okay, to get those, how can I get those tension forces together? Very good, Shabam. We're going to factor that out, okay? So we're going to say, yeah, it is. All right, so we're going to say US times tension force. No, hold on. No. Yeah, that's wrong. Yeah. Yeah. Wow.
I should just start teaching. I'm a pro at this factoring stuff. Here, I wrote the answer on the table in Grand George's class. I was right. Just wrote the answer straight up on the table.
Just straight up.
So like you're on the table. So on video, you're getting the instruction. Yeah. And then I erased.
Yeah. Okay. All right. Cool. Now, how do I get the tension force alone? Divide. Now, let me ask you a question here. Is it, since I've got mu s on top and I've got mu s on bottom, can I just cancel those out? No, I can't, because this one's adding and this one's multiplying, so you can't just cancel those out, okay? All right, so now let's go ahead and just start plugging our numbers in, all right? Mu was 0.4. What's the mass of that guy? 70 kilograms? What's little g? It's a naked number. Good. All right, so get your calculators out. If they're not already out, go through and type that in. Let's see what we come up with. How many sig figs should you have for your answer? Just one. Very good. Graham, I'm going to call on you to answer it in just a minute. One 1.4. Okay. All right, Graham, what'd you come up with? Very good. 200 newtons. Okay. Questions? You got it, Garrett?
Sometimes 1.4 is divided by 1.4.
All right, so now we're going to move on to pulleys. This is the last forces section. Yeah. All right, pulleys are a little bit different. I want to go ahead and talk to you about how you should approach them. Okay. When you look at a pulley system and it's asking you to find the tensions there, what you need to do is put a box around the pulley itself, okay? And that's your system. So right now we have a tension force coming off the top of that pulley here, and one pulling down on it here. So the pulley itself eventually is going to be a free body. What's the other free body in this problem going to be? That hanging mass there, okay? So let's do the box first, okay? And if that's going to be our free body, tell me one of the forces. Mark, which way? Which tension? What number tension? T2, very good. What's another force acting on the box? Which way? Okay. Is the box moving? No. So what do you know about T2 and gravity? They're equal and opposite, right? So what's the formula for gravity? mg. But they told me it's 26 newtons, so do I need to do anything? No, they already gave me the force of gravity. It's already in newtons, so I know that they gave me the force, not a mass. So that means that I know that T2 must be 26 newtons. Everybody good with that? What's up?
On the pulley itself.
Yeah.
So when you're doing the Freebody diagram, there would be two downward forces, the force of gravity, and that weight.
No, that is the downward force. Yeah. Okay, so now let's do our pulley. So we've got our 26 Newton force down here. And we have how many upward forces? 2. Okay, so let's see. Are those numbered different things? No, both T1. All right, so you've got 2 T1s both acting up. Okay, so that means that 2 times T1 must be equal to 26 newtons. How do I solve for T1? Okay. So what's T1 equal? This is why pulleys are beneficial. They reduce the amount of force that you have to apply in order to lift a heavy object. Okay? The total object was 26 newtons, but if you were pulling on one of those ropes, you'd only have to apply a 13 newton force in order to move the box. Okay? So that's good. Hey, yeah, just with a finger, you could lift a car. That'd be cool. All right. Let's look at this one. Okay. So in this case, again, what should we do first here with this pulley system? Put a box around that pulley. That lets us kind of see what's coming off the pulley there. We've got this tension force. We've got this one here. We've got this one here, right? We're going to ignore the fact that that force over there is at an angle. The reason that we are allowed to do that is because this rope is tangential to that circle. So it really doesn't matter which direction you pull on, it's always going to be tangent to the circle. Does that make sense? So there's really no difference in what angle you're pulling that rope at. It's always touching the circle at just one point. Because there's, no, not really. Okay. Now, how many free body diagrams do you think we're going to have to do here? 2. What's one of them going to be? The box. What's the other one going to be? The pulley. Very good. Let's do the box first. Why do I always, well, not always, but in this case, why do you think I'm choosing the box first again? Yeah, so I can figure out what this tension force is right here. Okay, that should help me out. All right, so tell me a force acting on the box. Which way? Okay. Tell me another one. Tension force acting up. Okay, and then gravity was equal to what here? Very good, 26 newtons, okay? Which means that this tension force is 26 newtons. All right, now let's do our pulley as the free body. Which way? Up, okay. Is that all it's acting downward? Bless you. That other tension force, right? Okay. So in this case, what do we want to say? Is anything moving? What's up, Adam? What do you mean? Oh, I'm just drawing them both downward. It doesn't. They're just down. That's all. All right. So if we're doing our F-net statements in the y-axis here, bless you, and that pulley system is not moving, it's in equilibrium, then what would we, if the first one was like mass times acceleration and it's not moving, what's the force going to equal? 0. Okay, good. Thank you, Siobhan. All right, and then the next one's going to be the sum of all my forces, right? Okay, so tell me what that's going to be, please. No, it's not just force applied because this tension force right here, that was the 26 Newton one, okay? The other one up at the top, that's holding the whole system up, right? So, yeah, exactly. If you go back and we look at the picture here, if we know that this is 26 newtons, and we're also going to be pulling down with some amount of force, doesn't matter what it is, but something, then, and this string right here is holding everything below it up, it's going to have to be something larger than 26 newtons because there's two downward forces on it. Does that make sense to everybody? Okay, what's up? You could, if you wanted to. In fact, I labeled that one wrong. This one's the 26 Newton force. Okay? All right, so that means that we could say here, yeah, I guess to deconfuse and demystify, we'll say that this one up here, that one's T1, and we'll call this one T2. That way we don't get confused here. Okay? All right, so we can say force of tension 1 minus force of tension 2 minus force applied equals 0 newtons. What can we do? Well, do you know what the force applied is? No, you don't. Yeah, we know that 26 newtons down there at the bottom, right? So, let's think about this. That top string is holding everything else up. And let's go back and look at our pulley. What do you see about this string here? What's it doing? It's just going straight over the top of the pulley, right? So this string here is that string there, right? So yeah, they have to be equal to each other. If this piece of string is holding up 26 newtons, then that means this piece of string has to hold up 26 newtons. Does that make sense to everybody? Okay, so let's come back over here then. And we can say that we're going to say force of tension 1, because that's the one at the very top, right? Has to be equal to force of tension 2 plus that force applied. And we know that the force of tension 2 and the force applied are both 26 newtons, right? So what's force of tension 1 going to equal? All right. Okay, so like I said, with these pulleys, it's a little different by putting the box around the pulley itself, and you can see then exactly what's coming off the pulley in whatever direction you're looking at. That kind of helps, but then you actually have to go back and analyze the pulley and look and see what's happening, what string's connected to what, so that you know if any of them are sharing the same amount of force on them. Yes, sir.
So you said that like pulleys were meant to make work easier or whatever, but why in this one is the force applied the same as the?
Because it wasn't looped over, a different pulley. It wasn't looped over any differently.
Okay.
And the benefit of having a pulley this way is that if you've got a really heavy box sitting on the ground, you have to bend over and you can hurt your back by lifting up that way. But if you tie your box to a string or whatever, you can remain upright and just pull straight down. So that can it helps with the mechanics of things. Yeah. No. All right. Any other questions over this problem? All right. I think this is the last one, guys.
Real quick.
All right. So,
3 boxes.
do what now? Yeah, we got 2 pulleys plus that box on the bottom hanging off of it. Potentially. All right. So let's see here. Let's do our free body diagram on the box first. Give me a force acting on the box, please. Mark? Which way? Good. Okay. And somebody give me another force acting on it. Desire? The what? Not tension 2. Those are 3s. Oh, I'm looking at the wrong one. Yeah, you're right. T2. My bad. All right, so force of tension 2. Okay, so what does that mean about force of tension 2 then? It must be equal to the force of gravity. So force of tension 2 has to be 26 newtons. So yay, we checked off T2. We know what that one is now. Okay. All right. Now let's look at this. I'm going to call this one pulley A, and we'll call this one pulley B, so we don't get confused on that. All right. So let's roll over here, and let's look at pulley B. Okay. So tell me a force acting on pulley B. Mark? Which one? What's the name of that tension force? T2, okay? All right, so we have T2 acting down. What else? Somebody else? Desire? Yeah, we have T3 pulling up. We have 2 of those actually, right? Okay. Is that pulley moving? No, so what do you know about those 2 things? They're equal, so that means 2 times T3 must be equal to 26 newtons, because that's what T2 is. So what is T3 equal? 13 newtons. Okay. Now let's look at pulley A. Okay, so we're doing a free body diagram on pulley A. We'll roll back over here so I can see it again. All right, so how many things do you see coming up off of pulley A? Just one. And how many are coming down off of it? 3 things are coming down off of it, okay? Now, let's kind of look at this picture here real quick. What do you notice about this piece of string? It's the same string, so what do you know about F here? It has to be equal to T3, which is what? 13 newtons, okay? Good. So now you can talk to me about what's happening to pulley A here. Somebody tell me one of the forces acting on it, please. Isaac? Oh, very good. T1 upward. Somebody else? Mark? Okay. How many T3s going down? 2 of them. Okay. And then that last one? F, and what do we know about F? It's also 13, so I'm going to rename it T3 also, okay? So is that top pulley moving? No, so what do we know? They're equal, so that means that T1 is equal to 3 times T3, which means it's equal to 3 times 13 newtons, which means T1 is equal to? I know. Look at how awesome we are.